Hi, I'm Matt Natove, Executive Editor of Plastics Technology Magazine, and welcome to another Plastics Technology webinar presented today by Novatech. Today's topic is Achieve Advanced Cut Quality and Precision with Rotary Knife Cutters. It is presented by Bob Bessemer, Vice President of Extrusion Technology for Novatech in Baltimore. Bob is a longtime inventor and patent holder in plastics extrusion. He joined Novatech in August of 2018 with a wealth of industry experience, having spent 37 years in engineering and commercial roles, first at Killian Extruders, now part of Davis Standard, and then 25 years at Conair. Most recently, Bob's primary focus has been on sizing and cutting equipment for medical extrusion. The major goal is better control of the variables of the extrusion process and to eliminate the so-called black art. Before Bob gets started, I would note that if questions occur to you during the presentation, type them into your question box at the bottom of the pane on the right of your screen. And now I'll turn the webinar over to Bob.
Hello, this is Bob Bessemer from Novatech, and today we're going to be doing a webinar discussing blades and bushings for rotary knife cutters. I must say this is probably my favorite subject. For years I've been kind of known as Bob the Blade. Hopefully you won't hold that against me. And we'll start with a presentation. And hopefully, and I've tried to put a lot of good slides in here with a lot of video showing AutoCAD rotations, showing how to design blades, but we will specifically talk about blade thickness, blade materials, especially blade shape, the importance of blade speed, and the extrudate temperature. And we'll go into a lot of detail on that. And then we will start talking about cutter bushings for both tubing. We will spend a lot of time talking about why we would bolt bushings together, and we'll talk about air feeds, and we'll also start talking about profile bushings and why you'd want to bolt those together. And I'm sure you've seen many blades for rotary knife cutters. I've been involved in this for over 37 years. And in the beginning, there were very few blades available. And we're going to discuss why we would change the shape of these blades in this discussion. And one of my first rules was always to try and use the very thinnest blade possible. When we're cutting something, you are displacing material with a rotary knife cutter. So you are moving that material. And the thinner the blade, the less heat you're going to generate, the less force to cut through the part. You do have to be worried about if the blade is too thin, that the blade can flex. So if you start getting an S type of a cut, that is from the blade actually flexing within the hole. So if we're looking at the bore of the bushing, where the tube is actually going through, if the blade can actually flex within the hole by the pressure of the extrudate itself, you will need to go thicker. Obviously, if the blade is breaking way too often, you'll need to go thicker. And we will discuss blade materials. When you go to more brittle materials on the blades, you will have to go thicker. But we are really looking at using these bushings to provide proper support for the blade. So these bushings should have a minimum gap between the blade and the bushings themselves, typically only 1 to 2 thousandths. So we're using the blades on both sides of the bushing, both upstream and downstream, to support that blade. Blade materials. The most common that people have used is a blue temper spring steel. It's a very tough material, and you can put a lot of torque on that material, and it will wear very nicely. But if you have a lot of impact, or you have abrasive material like Kevlar or fiberglass you're cutting, the spring steel will not hold up very long, and that's why people tend to use, they go to razor blade stainless. And typically in the hardness, it's been 57, 58. In many cases, I've had people knock it back to 54 to 55, so it's not quite as brittle. But as you go softer on the stainless steel grades, you will not retain the sharpness. But if you are chipping a blade, you're either going to need to go thicker, or you will, and if you're going harder, again, you will need to go thicker. I have used M2 in some cases and D2, and D2 will still rust. So, and so will M2. They still have rustable materials in them. So beware of that. However, both of those materials could be electropolished, and we will talk about electropolishing in a bit. As far as ceramics and carbides, I have used carbides for cutting some Kevlar reinforced hose, but again, you've got to go thick on that material because it is very brittle. And typical blade thicknesses have to go to 62 thousandths or even 1/8 of an inch in the carbide, so they hold up. But if you get the right thickness and the right shape, going to a better material is the way to go. When we talk about the blade geometry, you look at a double bevel blade. So there is an angle ground in both sides. It's very, very important with this type of blade that the bevels be the same length on both sides. If we're cutting a rigid part and the bevel is longer on one side, say somebody has hand sharpened it, that could cause the cutting to veer off. It will move with the greater side of the angle. And there are cases where I've actually gone to a single bevel blade for cutting some wire embedded product that we will discuss later in this presentation. When we're cutting a wire, whether it be copper or stainless or even spring steel, we've had to go a single bevel, and the bevel is all on the downstream side, so that we have a straight side facing the upstream bushing, so we're shearing against the upstream bushing, and we're using the downstream bushing to hold that blade so it does in fact shear, just like a pair of scissors against the upstream bushing. So that's one of the few cases we will use a single bevel, and we'll talk about that in a further slide. You'll notice that there's a single bevel and then a secondary bevel. In a lot of cases, to keep a blade from dulling too quickly, just like in razor blades that you shave with, there may be 1, 2, 3, 4, or even 5 different facets to edges. And by not having a long, sharp single bevel where the edge, it can roll over very easily, you put a secondary bevel to toughen that blade, and that will keep that blade sharper longer. But it may not do as well on cutting some very soft, flexible materials as you want. The longer, sharp bevel will actually do better, and we'll discuss that further. The blade shape. And I have this showing, and basically with a straight blade, we can chop with a straight blade, we can slice with a straight blade, and we will spend more time. We can then go to a curved blade, slicing, and in some cases a piercing blade. Today we're really not going to be talking about these piercing. In the old days they used to call them woodpecker blades and also bat wing blades. But I'm going to show you some other technology that would let you skip this, because the problem with these type of blades is this tip doesn't last very long. I've tried a lot of different things on this type of blade, but we will talk about changing the shape of the bushing to an oval, which we will spend a slide talking about later. And you'll notice there's blades that are being commercially made. These are all made by Cadence, but there are many companies, razor blade companies, that make blades. But you'll notice a notch on the back of this blade. So this is the cutting edge. This is the cutting edge. This is the cutting edge. We've relieved the back, and we're going to spend time about talking why you would do that, but we're cutting down the amount of interruption, the stoppage. So when the blade is cutting through your tube and it's passing through, we want to minimize how much stoppage this blade is causing. And you'll notice as we go to these slicing blades, this interruption can become pretty drastic. We need to make sure, and we'll look at a chart, because we can calculate this today, the exact stoppage a blade causes, depending on what you're cutting and the line speed and the blade speed. Now we're going to spend some time talking about chopping versus slicing. And chopping is the typical way that's been used for years and years. And people went to slicing when they cut softer durometer materials like hose, like medical tubing. Whenever you're cutting something very soft, the slicing action is much better. And again, we've spent a lot of time talking about the slicing. One thing that's important though, if my product is cold, and it's a rigid material like a rigid PVC or an ABS, if the material is too cold, the curved blade really isn't going to do much for us, because it's just like a wedge when you're splitting a log, and the wedge goes down and you start to displace the material, and at some point that log pops. In other words, the cut or the split will be ahead of the blade because the material is no longer being displaced, it fractured. So if the material is too cold, the curved blade really isn't going to do any advantage for you. You might as well stay with a chopping type of a blade. Again, we're going to spend some more time talking about this. This is the chart I showed, and I'd be glad to share this with individuals. You're welcome to call me and discuss at any time with me. But this is an Excel spreadsheet that's been developed for years, and it lets you look at what your line speed is, the cut length. It lets you look at the blade RPM. Many of the cutters today, you can actually adjust the blade speed from anywhere from 150 to as much as 2,000 RPMs. And to know how that calculates, you really need to know the distance from the center of your blade arm to the actual cut site. In this case, I put 15 inches. But on many, many cutters, it's between 4 and 7 inches, the distance from the center of your tube to the center of the rotating arm of your blade arm. Once we know that, we can actually calculate what the cuts per minute is, and we know what the bushing bore is, we know what the width of the blade cutting through, so we can actually calculate the part interruption time and the distance. So we know that we're actually stopping a part for 10 thousandths or 30 thousandths or whatever, because that's very important to know when we're deciding how far the cut site should be away from the puller. We've got to leave enough space between the exit nip point of the puller and the cut site to allow the material to deflect or bow while that blade is interrupting or stopping the actual flow. It's not like a traveling saw. Most rotary knife cutters are stationary. So if we can calculate that stoppage, say on a straw running at 900 feet a minute, and we know it's stopping for a 1/16 of an inch, we better allow enough distance, 1 to 2 feet, for that straw to bow ever so slightly, or we're going to cause undue wear in the blade. Sometimes you'll look at your exit bushing and you'll see a lot of wear where the blade is being pushed into the exit bushing, almost scalloping it. It's obviously going to cause premature wear on your blade also. Again, I can speak to individuals on this at a later date. Now, when we talked about the material, and if it's too cold, this is a clear sign. If you see whitening on your tube or your profile, and we'll look at some other pictures also, that is where we no longer were displacing. So the first half, the blade was able to displace the material, and the blade was either too thick or the material too cold, such that from this point on, we started fracturing. The problem is where you start fracturing, you see the fracturing here also. Typically, now a fracture is not square, so your blade, the cut will not look square. You may see a nice square cut, and then you have an angling off where the fracturing is not controlled. So the temperature is going to be something very critical, which we will discuss in more detail. Here you can see profiles. So obviously the blade came down from this side and it popped, breaking through the bottom, which is not giving you a square cut. You can see it here and you can see it here. So, and you can see what happens when fracturing occurs. You can fracture pieces out, tearing, and I can guarantee this kind of peels off. This surface is not flat as it started to fracture off. So again, clear sign that this profile was too cold while cutting. So if you see any whitening or even a hazing on a part, you're no longer displacing. The best thing you can do is vary your process to deliver the product to the cutter at a warmer temperature. And how to warm the part. The old days, and I've seen this so many times, people are using all kinds of devices to try and reheat plastic. The problem is plastic is a great insulator, and the insulation, it's hard to, you've done everything you can to cool it off, and now you're trying to reheat it. It's not a very controllable process. So I'd much rather see you control the rate of cooling in the process. And here I'm going to just back up once. If you know and you determine the temperature at which this particular material, And there are temperatures at which every material will cut. Rigid PVC, typically you can start to cut very nicely, anything over 110 degrees and go up to 135 degrees without causing distortion in your puller. You get to materials like an ABS, you may have to be up in the 180, 190 degrees, but you'll find for every material there is a temperature sweet spot. And if you can vary your process, not to cool the profile of the tube down as much, you can enhance the cut quality very, very nicely and have it be a controllable, repeatable process. Now, blade heaters, I have used them occasionally, and what you're doing is you're trying to sit the blade next to a heater to bring it up and have the blade hot. And use this, one of the best applications actually was cutting a vinyl cove base, and they had an economical filler inside and a really nice outer coating of virgin material with the color. And you could see a difference in the end cut, and they butt these parts up against each other when they're installing them. So what they did is a heated blade, and what that did was kind of smear the end cut and smear the surface so it all looked the same. So in that application, heating the blade worked very well. I've also had one on a polycarbonate. It actually helped minimize particulate. You've got to be very careful though, because heating a blade, the blade is traveling so fast when it's cutting through the part that the part, you stand the chance of material building up on the blade and getting particulate. So I'd say for most medical applications, be very leery. You're going to have to set the temperature properly. I have seen it help on some rigid PVCs. Again, melt some particulate and sear that off. So that's something you can look at, but I'd rather you talk to me specifically on individual applications. And now we're going to start talking about the chopping action. This is where I said I put some slides in here so you can really see a blade sticking straight out from the arm. You're chopping, and that chopping is putting a lot of undue pressure on the part. It also, if the blade starts getting dull, it can also be a particulate generator. And by the way, here you can see how this blade's been nicked away. This blade's been nicked away, but they're chopping. And that chopping action is going to flatten that tube as it's cutting and cause a lot of pressure and possibly try to drag material down between the bushings. Sometimes, say, cutting a silicone, you'll see a little C-clip looking little piece of particulate. It's actually where the blade pushed the part between the bushing, and the bushing actually cut the particulate off. The blade wasn't even sharp enough to cut it itself. And when you're cutting like this on a flexible, that blade has to be absolutely sharp to do a good job. Here's cutting a profile with the straight blade. And obviously you could rotate the profile to have the blade hit at the different spots. If this blade kept hitting that corner straight, you're gonna probably chip that corner of the blade where I'm first hitting it. So you do have to be careful. If the material is warm enough, a straight blade will do a job, but we will spend some time talking about why you'd go to a curved blade. Here's an example. I do this all the time, teaching chopping versus slicing. And that's with a very sharp razor blade. And you see how far down, how much pressure it takes to cut through this piece of material just by that straight push. When it's taking that much pressure, the likelihood of it dragging it between the bushings and tearing it off and or causing jamming or flattening the tube as you're cutting is very good potential. So this is something you can do with your own tube, and especially with a silicone or a low durometer of urethane. Chopping is definitely not the way to go. So what we do, we take blades, and again, many blades are available today, whether it's a Schick injector or whether it's some commercially available blades. In this case, this is a Medex blade made by Cadence. And you can see where we've made the blade, it's on an angle and the back edge is relieved. Now notice the other thing we've done here. We've machined part of the bushing face away so the blade arm can actually hold the blade closer to the cut site. Very, very important thing. I know you're limiting your cut capacity by doing that, but if you want to truly slice with a straight blade, you need to hold the blade very, very closely to the cut site. Another thing to see, these blades today, we are doing a treatment to these blades. They have been electropolished for medical applications. And what the electropolishing does is, whenever you're grinding a blade, you'll have grind marks, and the electropolishing will abrade some of the grind marks and smooth it out. And you'll end up getting less particulate because those grind marks, as you'll see in a further slide, those grind marks can be seen scratching the tube and creating particulate that will be seen as hairs. Now there's a Schick injector blade mounted on a real severe angle, and you can see we're really drawing the blade down through that tube. So even though it's a straight blade, because we've mounted that blade very close to the cut site, probably only 1/8 of an inch away, so we've really cut down or minimized the cutting capacity by doing this, we're getting a very, very nice slicing action. The most important part of the slicing is when the blade is exiting. The last part of the cut wants to be drawing the blade through, not pushing it out, if you're looking to get the optimized cut on a flexible part. This is an example. Again, you can see we've taken a blade. This was actually a cut down double edge, 4,000 thick Wilkinson double edge, which a lot of people in the medical industry use. They've actually cut it down and they've actually relieved the back. But notice the slicing angle they've put on this. So they're slicing as much as possible. And notice how much bushing has actually had to be relieved to the blade arm to actually clear the blade. The arm that's holding the blade is needing to be held very close to the cut site, very close, within probably 1/8, 1/4 of an inch of the holder. So we're able to hold and support a very thin blade. Holding a blade very close to the cut site will allow you to use a thinner blade. In many cases, we're now using a standard 4,000s, and some people are even going down to a 2,000s thick blade. Here's that same blade, and all I'm doing is holding it at about a 45-degree angle and slicing it down through. Notice how small amount of pressure it takes to cut that same tube as compared to that chopping action. This is what you want to try and replicate in your cutter when you're cutting flexible materials. When you cut a steak, you just don't push the blade down through. You draw the knife back and forth in a slicing action. You want to do the same thing with your tube. We don't want to be blocking off the tube. If we're using internal air, if you collapse that tube, you're going to be changing the diameter slightly. But by slicing, we will minimize jamming. Now here is a curved blade. So you can only go so far with a straight blade holding it at an angle. So I have had Cadence develop a slicing curved Medex blade, and again, available in 10 and 4,000s thick. And we have relieved the back edge to minimize interruption. And you can see here, you can adjust the blade in and out, and you can have it really slicing through. This next slide shows a blade that was developed for cutting pencils years ago, made of plastic pencils with plastic lead. And you can see how we optimized. And notice the last part of this cutting, how that blade is slicing right through the last little bit. And that blade was about 10,000ths, and easily the back edge of that blade could have been relieved. But I just wanted to show you, if you design a curved blade, and again, as long as you know the distance from the center of the blade arm to the center of the cut, we can calculate that out. And the old days I used to do it with, I made a paper model of the cutter and the blade arm, and I would actually throw arcs and design a paper blade. Today, we do it on either AutoCAD or SolidWorks or other engineering programs, but you can design and get a beautiful slicing angle for that particular part. With that, we'll start talking about cutting profiles. And again, with the properly designed curved blade, now this is cutting a fence slat, a tongue and groove. And again, I do have to be worried about interruption, so we need to design this blade, but keep in mind the line speed and how long, what the stoppage is we're creating by having that blade go through. But that blade was designed to slowly work its way in, not hammering into a corner, which is going to cut down on the life of the blade, but carving its way in to give us a very nice, smooth cut and a square cut without getting fracture. But that part did need to be 110 to 120 degrees to use that. And here was another profile, and these little tangs at the top of the profile were very delicate. So notice how we're carving through, we're getting a nice square cut, we're not hammering into the profile. So squareness and not breaking those little tabs off were very, very important. So again, you can see what we're doing with a custom blade. You could also rotate the bushing to affect the way the blade is entering the part. But on a part like this, we may have had to leave 2 to 3 to 4 feet between the puller and the cutter to allow for a little bit of deflection. Some people will put a little roller conveyor, a single roller in between, and have a slight bow up. So they're going to control that bow between cuts, that stoppage. Now, we're going to talk about cutting embedded wire. And whenever we're doing this, I've definitely used, we talked earlier on, using a single bevel. You're actually using a curved blade because we want to cut through the wire last. So what the curved blade did was actually cause the tube to slightly rotate as we were arcing through, and it would cause this tube to rotate, so the wire ended up being the very last thing we cut. But it did need to be a single bevel and a special material. And here's where we start talking about bolt together bushings. When we're cutting any of the profiles or tubes today, or especially wire embedded, you cannot gap the upstream and downstream bushings independently. You need to have a machined gap and hardened bushings. So if I'm using a hardened blade here, my bushings also are going to have to be at least D2 hardened, so that we're supporting a blade like this, because the bushing is just as important as the blade in the shearing. And again, I've had very good experience not only cutting copper, but stainless steel and even spring steel, and be glad to discuss that with individuals at a later date. We talked about the grind lines of the blade, very important for medical applications if you don't want to have scratch marks. And wherever you have scratch marks, I'll show you in the next slide, you'll see those scratches are where you're developing hairs. So the grind of the blade is very important, and that's why people have started to do electropolishing. So you can actually take these grind marks from a blade, and even a shaving blade, you can put it under high enough magnification, and you will, this is a Schick injector, you'll actually see the grind marks, and that will cause particulate as far as hairs. So electropolishing is a good solution, or taking wet dry 1000 or 2000 grit paper and further polishing that edge to get rid of the grind marks will help. Here you can see hairs generated from the grind marks. And again, that's a hair sticking out there. And those hairs are definitely from the scratching of the grind of the blade cutting through your part. In some of this, you can see a little bit of an arc. That was from the tube collapsing, a little bit flattening. So they may have, there's a little bit of an arc here, but I would say they probably were using a chopping blade, not a slicing blade, cutting through this part. So it kind of, you can see where the part was pushed down before the blade penetrated. Again, we worry about the edge of the blade, but also people using the Schick injector, you really don't want to be cutting through where there's a slot, because where that slot is can act as a cheese grater, again causing particulate. Another thing to look at on the blade, don't just worry about the slots, but worry about the back edge. People that make commercial razor blades worry about the sharpness, but they're laser burning the shape. So a laser burn, you can have a burr back here. So I recommend taking a blade, even out of a razor blade pack, and laying it on some 1000 grit paper, wet dry, or a stone, and laying it flat and making sure there's no burr on the back edge. And again, if you have this, a lip like this, most people will actually laser or EDM this away. So they'll remove this section so they're not cutting through a slot. When you see a film on a profile or tube, that's typically generated from heat. It too is particulate. So when that blade is cutting through, if it causes, the blade will start to heat up over time, and it gets warm enough, it's going to be melting some of your plastic. Some of that plastic will end up on the blade. Then the next cut, that plastic that resides in the blade is going to wipe onto your next cut, and that's what you see right here. So we need to worry about that. So we're going to be talking about how to lubricate the blade to prevent this. And we're going to talk about a lot of different ways to lubricate. And I've seen a lot of people, some people have a piece of felt or a piece of sponge right above their bushing, and they'll just drip water or alcohol. If it's a non-medical, I've seen people use things including diesel fuel, kerosene, or even glycol, antifreeze, to lubricate their blade. You're wetting your blade to decrease drag. You're also keeping the blade cool. So almost on any material, I'd recommend in some form wetting your blade and we're going to also talk about wetting the bushing, but wetting the blade is a critical thing. In many cases, there can be a blade lubrication tray built into the cutter, so as the blade makes a rotation, it will actually pass through a reservoir or a tray. Or in this case, this is a removable one for medical, but there is a tray, so as the blade is making its cutting cycle, the tray is open right now. It would be moved over here, and we would maintain a level of either distilled water or alcohol in here, and let the blade pass through that. If there was particulate, hopefully it will wash off in the tray and will cool the blade. So it's kind of a blade wetting system. We have used a felt pad up here as a blade wipe, and it can be a FDA white material, which is a felt. But in many cases, I've had this felt then stick to the blade and pass on to the next cut. So it's particulate. So I'd much prefer to have the blade be wetted other than using a pad, but there are cases where you've got to have a blade wiping system where you're wetting a pad and wiping the blade through it. And we can do a lot of things to wet the blade. Here, we're actually delivering lubricant into the cutter bushing. Here we got an air feed bushing, and we're wetting, and you're going to see a blade wipe on this first slide. So the blade is passing through a wipe right here. So we're dripping alcohol onto a felt pad, so the blade is constantly being wiped and wetted. Here you're seeing a mist being put onto the blade intermittently. So they're wetting the blade right on the cut path. And in this case, we're actually doing a fogging. So we've actually created a mist or a fog between the bushings as a bushing wiping wetting system. And again, I'll be glad to talk to individuals what might be best for your process. We also want to wet the bushing, whether it's with a spray mist or dripping alcohol or liquid into the upstream bushing. What you're doing is decreasing the friction. So the tube going through, in this case, it's even going through a Delrin or a Teflon bushing, an insert into the bushing, because it has less drag than a piece of stainless. But wetting the bushing to help the product slide through is going to enhance your cut tolerance and minimize jamming. When we look at cutter bushings, if you start seeing marks like this or little tears at the bottom, this is a clear sign typically that the bushing gap is excessive. Where see this little tab, it actually drew down between the bushings. And both faces of the upstream bushing and the downstream bushing should be sharp. If you've taken the exit bushing and rounded it so the part moves after it's cut into the downstream, you're hurting yourself. It's just like having a dull pair of scissors. I'd much prefer to see you have a 5/1000 larger bore on your downstream bushing than the upstream bushing. That way you've got two nice sharp faces, and when the cut tube goes through, it doesn't hit. Commonly, you can watch the tube if you're cutting short parts. If you see them exiting the exit bushing, and they should come out nice and smoothly, and you can just strobe it almost. But if every once in a while you see what I call a shooter, a part shoots out and the rest of them are falling nicely, more than likely the piece is catching on the exit bushing. It's a bushing problem, and you need to work on your cutter bushings. Having excessive clearance in the bushing is a big problem, and that's going to cause what I call penetration mark. The blade will push the part down until it is the same shape, and many times you'll see penetration marks 180 degrees apart from each other where the tube was almost flattened before actually the blade penetrated it. So having a bushing bore fit the part, and again, if you're cutting a rigid part, the tolerance may want to be within 5 or 10 thousandths. If I'm cutting a very, very flexible part, I still probably need 30 to 50 thousandths clearance, and that's why it's very important to have a slicing blade so I'm not putting a lot of downward pressure. Good examples here, you can see penetration mark almost 180 degrees apart. Obviously the bushings were way too excessively clearance, and here you can see the part was not only cold, but the blade was pushing it down quite a bit to cut through it. Bushings, the proper face. Here you can see we relieved a little bit of the bushing face so the blade arm can fit inside. I try to leave a minimum area, but you typically want no more than 1/8 to 1/4 of an inch from the bore out before you start to relieve it back. That way you can gap the bushings very tightly against each other. It's kind of hard to see in the gap if the space is that wide. So I don't really need anywhere near this amount of support, but at least 1/8 to 1/4 of an inch worth of support on the outside of the bushing, and then angle it back maybe 30 degrees. It's a lot easier to see the gap. But notice, nice sharp edge on the upstream and downstream bushing. Sometimes we will, and you can see here, it's a little easier to see where we've got that little 1/8, 1/4 inch of land, and then the rest is machined back on a 30 degree. And here you can see we relieved a long way into the bushing, so the blade arm can be holding the blade and get a nice slicing angle. And here we have put a Teflon or a Delrin insert in to further decrease the drag and help as a snout to support the tube further closer over to the puller. Now, bolt together bushings. For years and years, everybody has just taken a downstream bushing and you slide the downstream bushing up to the blade and touch the blade, but don't deflect it. And then you lock this bushing in, and then with the blade in the middle, you slide the upstream bushing and slightly hold it against the blade and lock it and make sure that you can still slide the blade through. But really, we want no more than 1 or 2 thousandths bigger gap between here than the actual blade thickness. And it's very difficult for operators to get that gap right, and it's a variable. Also, the alignment from the upstream bushing to the downstream. A lot of the bushing holders have 3 to 5 thousandths clearance, so it's easy to have, say, the downstream bushing slightly cocked so the downstream hole isn't perfectly lined with the upstream. This is why we're going to just actually bolting and pinning the bushings with a pre-machined gap. This way your bushing alignment is perfect and your gap is perfect and repeatable. And this is how it was done with an offset bore, but you can see how actually there's a pin, there's 2 dowel pins with a bolt for bolting them together, but a land has been created here. If it's a 10 thousandths blade, we'd have an 11 thousandths land. So when you bolt these and pin them together, you've got that perfect 11 thousandths gap, but better yet, you know that the bore is perfect. And again, if this bore on the front was 125 thousandths, the exit bore might be 130, so 5 thousandths bigger. It's an old trick learned from high-speed straw manufacturing years and years ago. Straw bushings have for years been bolted and pinned together. This is a straw bushing, and again, they were offset, and they were pinned, and matter of fact, this was showing where a drill bushing was able to be put in, because cutting straws at such high speeds, up and over 1,000 feet a minute, they couldn't stop a line to be changing bushings and changing blades, so they put hardened drill bushings in here. And again, everything was bolted and pinned, so the gap was predefined. And again, it's just talking about the ability for inserts. In this case, by the way, you're going to see an oval shape. We'll talk more about this. If you have a profile or an oval, even more important for the bolting and pinning, so that you know the upstream and the downstream bushing bore is going to be perfectly aligned. This is showing particulate generated on a bushing, and I know this one actually was a chopping blade, and you can see the little dust and particulate all hanging below it, so you know some of that particulate is going to be on the part. So there have been cases where we've actually provided misting, going in and a mist between the bushings, trying to spray off both the blade right before it's making the cut and keeping the surface between the bushing clear and being wetted. Notice how narrow this is, so it's easy to wash the surface to get rid of particulate. And air feed bushings. For small medical, this has been done as many as 10 or more years ago, and you're actually creating a little venturi. So figure a needle valve, and there's your needle, and this is threaded, so it threads in against the seat. So what can happen is when the air comes in, it actually, and this would be threaded in, the air comes in and goes around this needle. Once you crank it open just a little bit, the air goes out, actually causing a little bit of suction. But better yet, once the blade has gone through, so when the blade goes through, it stops the air movement. And as soon as the blade clears, that air, it will push the cut part out, which is a very good thing for cutting small flexibles. If you don't have air, the new tube is going to have to push the cut piece out, which can cause jamming. So the air, just as beneficial to help actually draw the part into the cutter bushing, it is even better for ejecting the cut piece. In many cases, even with an air feed bushing, and a general rule is whatever the bore is, the bore needs to be 30 to 50 thousandths larger than the actual tube. And again, critical reason for using a slicing blade. That's why the milled so much relief here. So a slicing blade using an air feed bushing will dramatically help your process. The bolt together bushings, again, this was done years ago for cutting an angle. Again, it had to be cut, and in this case it was just a single angle, but in some cases there'd be three-piece bolt together bushings. But again, you can see it very precisely holds the gap and the angle and has the bushing faces perfectly aligned as a pre-assembled. It's almost like sliding in a single bushing. We were going to mention about cutting using an oval bore. If I have a tube, a relatively thin wall, like a butyrate tube or a polycarbonate tube, that I'm getting a flattening, the penetration mark. If you take that same tube, and I did this years and years ago for a caulking tube where it had to be square cut within a 10,000th of an inch at 100 feet a minute. And if you take that tube and slightly squeeze it, making it egg-shaped, and push the blade against the tip of the egg, just like I'm pushing against a straight blade on the side of a round tube, if you try to push in on a round tube, it'll flatten pretty easily. But if you make it partially egg-shaped and push in from the end, the top of the egg, like here, you've made the tube stiffer, and you'll be amazed at how much squarer cut you can receive. And you don't need to use a woodpecker or a batwing blade. You can use a straight blade. Don't use a slicing blade in this case, and use the actual material, the strength of the material, to cut with an oval. And again, if you're going to do an oval bushing, I highly recommend going to a bigger bushing holder and doing them as a bolt together so you can ensure alignment. This was done with an oval bolt together bushing, and now you can see what we did slicing through. So on cutting some very thin wall, larger diameter urethanes, I have made oval bushings and done a slicing blade, and this was very, very successful where people were having to cut it offline. So I'll be glad to talk to people at a later date individually on their particular application in order to be able to cut some of these larger diameters, some of the medical tubes for putting doing operations where they're not cracking your whole chest open, they're putting heart valves in, and the tube can be as big as a ½ an inch, and the wall can be only 5 to 10 thousandths thick. So difficult cutting a soft, low diameter urethane in line. Profile bushing, same thing. You're making a shape, you're EDMing the shape. I highly recommend to be bolting them together. You design the blade so the blade only comes up this far. So you can have a land, the blade clears, but now my alignment can be perfect. Again, I can make the exit bushing a silly 5 to 10 thousandths bigger the whole way around. So it goes through, and I can maintain that bushing gap. Again, there's the fence slat bushing, again, bolted together. And we designed the blade around it. And here's another one. Again, bolted together. So it can be done with a round bushing or rectangular bushing, but bolted together, and you can EDM in the shape and be very supportive and maintain the specific gap for that blade thickness. It's going to help your blade last a lot longer. And again, if you're going to be bolted together, I highly recommend going to a tool steel that can be hardened. And a lot of the bushings are round, so keep in mind that if my blade, even a curved blade, is hitting into that corner, I'm going to probably wear a chip into that corner of that blade pretty quickly. I simply, for this application, I rotated that part just slightly so the blade didn't hit into a corner. It eased in along the whole bottom of the profile. I got a very square cut. When I did this also, I was getting a little push in on the corner. And for the assembly machine, it was causing difficulty. Simply by just barely rotating that tube so the blade didn't impact the corner, I was able to get a perfectly square cut and not get any distortion in the corner of this particular, it was a fence post. And cuff detecting bushings. Just another type of a bushing. A lot of times they are very flexible. They can be warm when you're cutting, so I highly recommend having a Teflon insert. You can see how little stainless. I still want to shear against the stainless, a hard surface, but the rest of this bushing is a Teflon insert. And it's very, very critical that this tube slides through nicely, because you'll see in the next slide, we're using very small 27 thousandths blue beam looking through here to detect the corrugation to tell us where to cut. So you don't want this kind of chattering as it slides through. So it was very critical that the size be right of the bore, plus have a Teflon insert for us to repeatedly detect it. And again, I'll be glad to talk to individuals on this type of application at a later date. And I very much thank you today. This is one of my favorite subjects to talk. I could probably do a talk for 8 hours. And I've gone into many facilities and spent 8 hours doing training classes. I'd welcome you to give me a call at any time, and I look forward to answering your questions. Thank you so much.
Well, thank you, Bob. There's an awful lot of detail there. We do have some questions. When cutting rigid profiles, sometimes operators dull the blade to minimize fracture. Is that a good practice?
It is, but it's difficult to repeat. It's funny, years and years ago, I went to a company called Specialty Blades, and I said, you know, just like dulling a nail so I don't split wood, I've had customers dull a blade so they don't fracture, say, a rigid profile or a rigid PVC chip carrier tube. And they would literally dull the blade against some paper, and such that you couldn't cut yourself. And I wanted him, as a blade manufacturer, to sharpen a blade to the same effect. And he said, well, this is not going to be repeatable. And what he did was a better solution, was vary the secondary bevel. So they had a long bevel and then a secondary bevel that did the same thing, but it was highly repeatable. So I'd highly recommend talking to a blade manufacturer and working, and I'd be glad to speak to individuals on that directly.
Okay. Are there other cutting methods other than rotary knife cutters for tubes, especially HIPs, high impact polystyrene?
Absolutely. You can only do so much with a rotary knife cutter. There are other forms of cutters, one of them being planetary cutters that are used very commonly in the pipe industry, and others have started to manufacture them for cutting smaller items, including HIPs. We're just like a lathe, so we can't rotate the tube, so we rotate the cutter head around it, and they can be parting type blades or rolling type blades. But it's very important when cutting a material like HIPs to bring the blade in at a very controlled speed. So it can't, it has been done with air, or aerable oil is even better, but even better to be done with something such as a servo actuator.
Okay. Now, what if somebody is getting black specks on their medical tubing? Where are they coming from?
Well, the black specks typically aren't from the tube itself. Typically, they're coming from the belt puller. Depending on the type of belt, it could be the belt covering material, whether it be a black sponge or a neoprene. But in a lot of cases, with a poly V belt, they could actually be from the V grooves of the poly V sheave cutting into the underlying carcass of the belt. And they will fall down, and sometimes they can fall onto the tube or on the belt and then go on to the product.
Okay. And what is the optimum distance between the puller and cutter for cutting rigid tubing?
Well, a good practice, as I've done, and again, we could be mathematical about it and use the chart to actually calculate the interruption. But what I've done is you take your fingernail and lay it on the product as it's entering the puller. Obviously, be safe when doing this. Don't put it in the puller, but put it in front, somewhere between the tank and the puller. And you should be able to put your fingernail, and when you make a cut, you should not feel the shock back of the actual cut. When you're too close, when the blade cutter is too close to the puller and there's not enough room for the material to deflect between the puller and the cutter to bow, it will cause slippage in the belt or cause backlash in the belt drive mechanism. So again, a good rule is use your fingernail and keep moving the cutter further away so you don't feel the shock of the cut at all.
Okay. Now, we have a couple or three questions here that are a little bit off topic. I don't know if you want to address them now or offline, but couple of people are asking about blades for pelletizing and for slitting or cutting sheet. Is that anything you want to address
Yeah,
here?
I will certainly attempt, and if I can't, I'll be the first one to admit it.
Okay. Uh, well, basically the question was, what type of blade should we use to optimize cutting in a strand pelletizer?
Well, a lot of it depends. There are different types of strand pelletizer. This typical strand, you have a bed knife and a shearing blade. And those typically will be single bevel blades, and they have to be gapped within 1/1000th or so because you are shearing the part off. And I was taught many years ago, just like in rotary knife cutters, what they do is to stop getting fracturing. So if you're cutting a pellet and you're getting a lot of fracture and a lot of fines, your product is probably too cold and you need to what they call condition the pellet. And that was done simply by shortening the line or elevating the water temperature in the water trough feeding to the pelletizer. So again, using some cutting the part when it's warmer should let the blade displace the material, and that will greatly, now you'll be cutting it, displacing it, and reducing the fines.
All
Hopefully that
right.
helps.
Okay, well, very good. If you want to tackle sheet, the question concerns they're actually slitting the sheet as it comes out of the die using a standard utility knife and a holder, and this is producing edge flare on the sheet, which they have to deburr later. And they're wondering if there's any information available on maybe substituting circular rotary knives for slitting the sheet.
Well, the first thing, if they're getting edge flare, it's telling me the blade is too thick. And typically sheet is 10/1000ths or thicker, where film is 10/1000ths and below. So if they're truly cutting a sheet and it's say 10/1000ths, 15/1000ths or more, typical blade would have been a Duesenberry blade, like a slitter. It's almost like a Stanley razor blade. And those blades are typically 25 to 35 thousandths. My first recommendation, depending on the thickness of the sheet they're cutting, is to try to go to a thinner blade. And a circular blade is a good solution. You can let it roll. But again, I think the thickness is going to be the main thing. So I see what the blade thickness is and try to go down maybe a silly 5 or 10 thousandths. It will reduce that amount of flaring, that displacement.
Okay, well, very generous of you to address these off-topic questions. I think we'll have to call a halt here, and I want to thank the audience for their questions, and any that we didn't get to, Bob will get back to you after the webinar. So thanks again, Bob, and thank you to our audience for attending today's Plastics Technology webinar. I hope it was valuable for you and gives you some ideas on how to improve your company's efficiency and competitiveness. This webinar has been recorded and will be available by tomorrow or even sooner on our website, www.ptonline.com/webinars. Within a couple of hours, attendees will also get an email with a link to the recording. Now, the next Plastics Technology webinars will be on October 9th at 2 p.m. Conair will present using Industry 4.0 to reduce maintenance cost and increase uptime. And the following day, October 10th at 2 p.m., ASAClean will discuss how to implement a purge program and stop wasting money. So for more details on those and other webinars, look under the Events tab on our website, www.ptonline.com. So thanks to all and good afternoon.